Hi there, welcome to this video. Thanks for clicking on. Hopefully it's going to help you with your maths revision, giving you a question on pure, stats and mechanics, the three different strands that you're tested on at A level, giving you some time to have a look at the question, how would you get started with that question, and then going through the answers. So let's get started. Have you been finding when you're reading questions you just don't know where to start? So what I've done in this video is giving you some questions, giving you some time to have a think about what you would do with that question, and then I've given you some hints and then given you the answers. So let's get started. So did you spot in this question we're looking for two real roots, we've got a quartic and we're asked to give the roots in exact form. So when you see the word roots, you are looking at the discriminant, b squared minus 4ac. When we put that in the quadratic formula, the fact that we've got a positive here in the discriminant means that we've got two real roots. When b squared minus 4ac is equal to 0, then you've just got one root. You've got the type of quadratic that sits on the axes. When b squared minus 4ac is less than 0, you've got the type of quadratic that sits above. When b squared minus 4ac is greater than 0, you have two real roots. Now they're all quadratics, and I'm talking about the quadratic formula. You need to think of a way to get this quartic in terms of a quadratic. So using that fact that b squared minus 4ac is above 0, we can rearrange and take this 4x squared to the other side, and then we have a disguised quadratic if we just let y equal x squared, and then we will have a quadratic. Factorize and then get what y is, then use the substitution back because y stood for x squared. There's no real solutions when x squared is equal to minus 1, so just taking the square root of 5 is our x, which is in exact form. When you get exact form, it's usually meaning that it's a surd. So do you remember the key formulae and the notation? This B dash here means not B. So the probability of A intersection not B, just on the Venn diagram, means the A on its own is going to be 0.2. And then this B with the line A dash means B given A dash. So that's conditional probability. What is the probability of B happening given that we're already in not A? So did you get your diagram something like this with filling in A intersection not B? So that is this bit here where we're not in B but we are in A. It's 0.2. A has to add to 0.45, so these two sections need to be 0.5, so we've got 0.25 in the middle. B has to add to 0.3, we've already got 0.25 in the middle, so the B on its own has to be 0.05. If you add those three numbers up in the circles, they come to 0.5, so we've got 0.5 on the outside. So then, because we're being asked this question here, probability of B given A dash, you need to use your conditional probability formulae. This line means given, so A given B means that where is A and B intersecting, divided by the fact that B has already been given, so you must divide by that second one, the one that's after the line, because we're already given that B's happened. So in terms of what we're being asked, B given A dash is going to be where the two intersect, divided by the second one. So where does B intersect not being in A? That's just the bit on its own here, 0.05, divided by A dash. Well, A in the question was 0.45, so A dash is 0.55, and dividing that 0.05 divided by 0.55 is 1/11. So keywords here, we've got connected particles, light string and smooth pulley. So there's no weight in the string and there's no friction on the pulley. We need to have our connected particles diagram, fill in all the details, and then see if we can solve the simultaneous equations and find the value of m. Did you get your diagram something like this? So the masses 0.2 and m are connected by the light string. The system is released from rest. Now we're told that the 0.2 mass moves upwards, so therefore the m1 must move down. Now what's taking it up is this tension, which is dragging it up. That's the driving force for the 0.2, but on the other side it's acting, it's moving down, but it's got the weight of the fact that the 0.2 is connected on the other side is dragging it back up. So doing the equation of motion, Newton's second law, for the one we know most about, what is driving it up is this tension. Taking away what's trying to bring it back down is the 0.2 G. So I always start with my forces, whatever direction it's going, that's the one that you do first, which is the tension, taking away anything that's opposing that motion, and we're just applying F equals ma here. Now because we know t, usually you set yourself up with some simultaneous equations and solve for a and t, but we know t, we don't know m, the weight of one of the particles. So what you need to do is put that t is 2.26, we know that g is 9.8, and just rearrange that one formula to get what A is. A is 1.5, and that will be meters per second squared. And then in the other equation, what is taking the m side down? It's the mg here. What is opposing that motion? It's the tension in the string, because we've got the connected particle the other side. So it's taking away the t is equal to ma. Now all I've done here is taken that minus 2.26 to one side, the ma to the other side. You'd have mg minus ma. Taking m out that we need to find as a common factor, we'd get this next line. M is into g minus a gives us the 2.26. G is just 9.8. The a is 1.5 that we found previously, and then just do 2.26 divided by the 9.8 minus the 1.5, and that gets you that answer there, and that's to 3SF 0.272 kilograms. Thanks so much for watching. Do like and subscribe, and check out the channel for some other videos to help you with your revision. You can always leave a comment if you'd like this format, or you have any questions, do leave a comment, and I'll see you on the next one.